Today we're going to discuss the kinetic molecular theory of gases. Kinetic molecular theory, or KMT of gases, describes the behavior of the gases based on their motion. We're going to refer back to this and to pressure over the next few days as we discuss the laws that govern the behavior of gases. The kinetic molecular theory involves four main assumptions. Number one is that all particles are in constant, rapid, random motion. So please remember that phrase, that phraseology: constant, rapid, and random motion, random movement. That means that they're moving fast, they're always moving, and the movement is relatively random. Now, this is responsible for mixing of gases. All gases left to their own are going to mix together, and responsible for diffusion and other behaviors that we're going to discuss in a few minutes. All gas particles move in a straight line until they collide with another particle or with a container, and then they change direction, and we're going to talk about what happens when those collisions take place. Okay, so particles are also small compared to the distance between them. What this really means is that we can ignore the volume of each particle, that the particle size is nearly zero compared to how big the distances are between them, how big the volume of the container is, the amount of space that these particles are allowed to occupy. This allows gases to be compressed, unlike liquids and solids where the particles are really close together. Gases, the particles being far apart, allows them to be pushed closer together because there's a lot of space between them. So when we take and we apply a pressure here, apply a big pressure on that, we're going to decrease the volume of the container. We'll talk about that in Boyle's law in the next few days. Decrease the volume of the container, but notice that the size of each particle doesn't change, only the size of the volume that the particles are allowed to exist in. Also, because of this large space between them, particles rarely interact, and interactions are really going to be thought of as collisions, and we're going to use that over the next few chapters as well. Number three is that particles don't attract or repel each other. They don't exert any sort of force on each other or on the other particles, and in this case, they behave like billiard balls in what are called elastic collisions. Elastic collisions, there's no loss of what's called kinetic energy. We'll discuss this on the next slide. What this means is that gas particles continue to move basically unimpaired. This also, though, we'll see that over the next few days when we start to discuss the behaviors of non-ideal or real gases, we'll see that these two assumptions are not always valid, and that there are certain conditions under which we're going to have to take into account both the size of the particle and the attractive forces between them. Fourth and last, and this is an important one, is that the temperature measures the average kinetic energy. We say that the temperature is proportional to, that's what this little funky looking symbol here looks like, is proportional to the average kinetic energy. This is a crucial point, and we're going to return to this point over the next 3 units. So make a note of this, staple this to your forehead, write it on your forehead, do something in which you understand that kinetic energy is measured by temperature. Temperature measures the average kinetic energy of particles. The kinetic energy is due to the motion of particles. So particles are always in motion, as we saw before. And the kinetic energy, this is a physics equation. You don't have to memorize, or we're not going to use this in any problems, but I do want you to see this equation, and we're going to use a rearranged version of this equation in a couple of slides to discuss some of the important changes, how changes in certain properties affect the changes of the behavior of gases. And motion is equal to energy. Now, temperature is proportional to kinetic energy. Kinetic energy, in turn, is proportional to the average velocity squared. That VAVG means the average velocity squared. And so we get a dependence that as the temperature increases, the kinetic energy increases, and the average velocity of the particles increases. And here's a plot that shows that for helium atoms, as we go from 0 Kelvin, we'll talk about the Kelvin scale over the next few days, all the way up to 300 Kelvin, which is just about a warm or hot summer day. All right, so some important properties of gases that come about from kinetic molecular theory are diffusion and effusion. Diffusion is probably a familiar concept to most of us. If you've ever smelled anything, any cooking or anybody wearing too much Axe walking down the hallway, that's an example of diffusion. Diffusion is movement of one material through another. So it's two materials moving through each other, in this case two gases, gas 1 on the left, gas 2 on the right, moving through each other. We're going to see that these representations of the gas molecules where gas 2 is moving faster than the gas 1 is going to be important to us on the next slide as well. Less familiar to us is the concept of effusion. Effusion is the concept of gas escaping through a small opening. For instance, the escape of helium from a balloon. Ever notice how latex balloons tend to lose helium very quickly? And that's because of the concept of effusion. And in effusion, we have one gas moving through a small opening. In scientific experiments, we can have them going into a vacuum, but that doesn't necessarily have to be the case. In effusion, we can control the variables easier, and that means that we scientists tend to use this to measure the differences in gases. We can actually use this to measure the molar mass or the molecular mass of an unknown gas from its effusion rate if we know effusion rates of known gases. This is called Graham's law of effusion. And again, I don't need you to memorize how to do this. We're not going to do any problems with it, but I just want you to understand that this kind of a process can be used to do scientific experiments to determine the masses of gases. Now, this is an important slide. What factors affect the rate at which these things happen? Now, remember, rate is the velocity. The velocity of a molecule is its rate. And the average velocity, we're going to talk only about average velocities in this slide and in this unit. The rate at which something happens, or the velocity, depends on the temperature of the system and the masses of the particles and the molecules. In this is just a rearrangement of the kinetic energy equation, putting a couple of other variables in there. Again, we don't need to worry about the actual form. You're not going to be asked to solve any questions about this, but there's two important dependencies that I want you to see here. The first is that since temperature is in the numerator, what this is showing us is that as the temperature goes up, so the rate is directly proportional to the square root of temperature. As the temperature goes up, the kinetic energy of molecules goes up. Okay, so hopefully you remember that. Temperature and kinetic energy directly related to each other. Temperature measures kinetic energy. And as the kinetic energy goes up from the kinetic energy equation, the average velocity must also go up. And here's a chart that shows the next dependence. And we saw the temperature dependence on the slide 2 slides ago with the helium. The other important dependence, and this is where Graham's law comes from, is that the molecular mass, in this case mm can refer to molar mass or molecular mass, but since we're talking about individual particles, let's talk about molecular mass of the particles. So the rate of the effusion or diffusion or any of the processes, which depends on the average velocity, is inversely proportional to the molar or the molecular mass, which means that that's down on the denominator side. So what happens here? As the mass goes down, as the denominator here goes down, as this part goes down, the whole thing goes up. Now, we're assuming here that the kinetic energy stays the same. And remember, what does that mean? Kinetic energy stays the same means that the temperature is being held constant. So if we're going to compare the masses of gases and their rates, we have to keep temperature constant. So as the mass goes down, the average velocity goes up. The opposite is true. So as the mass goes down, the mass is going down here, the average velocity is going up. We could have said it the other way. As the mass goes up, the average velocity goes down. Now, there's a classical experiment that shows this. We can take a system in which we have hydrochloric acid, basically soaked on this sponge, or our cotton ball right here, and ammonia on this sponge right here. And what's going to happen is that these two gases are going to diffuse and meet somewhere in between the two. And if you didn't know anything about the speed at which the gases are going to fuse, you'd think they're going to meet in the middle. But because, and they're going to form, by the way, when they react, they're going to form ammonium chloride. But because of the relative rates at which they fuse, the ammonia fuses faster than the HCl because it has a lower molecular mass. So this moves faster, and it gets further down the tube, and so where these two meet is going to be closer to the HCl source than to the ammonia source. Okay, so this is a classic experiment, and there are actually videos on this on YouTube if you're really interested and want to see this. Okay, finally, talk like a duck. How do you make something talk like a duck? Well, we use helium, of course. Now, why does helium make your voice sound funny? The scientific reason is that because helium, with a mass of 4 AMU for each molecule, is 7 times less mass than the mass of air. Here we're using 29 AMU as about an average of 80% nitrogen and 20% oxygen in the air. So, what should happen to the average velocity of the helium? You're going to go watch the video, and that's right here. And you can either watch the video now, it's next, or you can wait and watch this after you get through this slide. It's up to you. But this video is next in the playlist. So why helium makes your voice sound funny? By the way, it's not because it makes your vocal cords move faster. That's a common misconception. Your vocal cords don't vibrate any faster. Instead, as the mass of the helium goes down, or the mass of the gas that you're breathing goes down, the average velocity goes down, and so the average velocity goes up, and so the resonant frequency of your voice also goes up. Now, if we can do something with helium, you think we've got something that's called an anti-helium? Well, we sure do. We have something called sulfur hexafluoride, SF6. How much more massive is it than air? Well, if you do the calculation, it comes out to be 146 AMU is each molecule, which is about 5 times more massive than air. Now, I know in the video they say 6, but if you do the actual division, it's about 5 times more massive. That doesn't detract from the actual conclusions here. So the opposite of what happened above is what's going to happen here. As the mass of the molecule has gone up, the average velocity of the molecule must go down, assuming temperature is kept the same. Remember, kinetic energy and temperature being kept the same. So because of that, the resonant frequency goes down, and your voice gets deeper. And you can see this in the video. That's the third and final video in the playlist. Notice in the video, also watch after they get finished doing the breathing, you can also use the SF6 to sink a boat. And this is some pretty cool stuff. So hopefully you're going to get a lot out of this unit, and we will see you in class.